All right, everyone. So in this video, I wanted to take a second look at the work done by gravity, right? And I wanted to look a little bit more in depth as to why it is uh, what it is, right? Quite simply, we'll end up with the work done by gravity being equal to negative the change in potential energy, right? Or negative delta U. So let's see really where that comes from, right? In last week, I only did a video just in the y direction, right? And I showed that it was in fact negative delta U. That also holds here, but let's do an example where we take an object, whatever it is, doesn't matter, and it starts at point A and it goes to point B, right there, however you want it to, right? It can take whatever path, right? Whatever path is necessary, right? Or it doesn't matter, whatever path. So what I've written here is point A is at some position XYZ, right? And I've tried to denote it. Note this is also a right-handed coordinate system, right? If you put your pointer finger in the X direction, your middle finger in the Y direction, and your, let's see, thumb, yep, in the Z direction, right? That should line up with XYZ. And I did that on purpose to put Y going up, right? Because that's what we're used to. So point A has some X position, has some Y position, and it also has a Z position, okay? And then it's going to point B that also has a different, it also has X, Y, Z, but they're different, right? X, then it's Y, and then it's Z, okay? Again, you don't need to know what those numbers are, and for energy, it doesn't matter, okay? I'll try and explain a little bit later that the numbers we plug in don't matter. What matters is the I guess the formulation, right? The simple fact that this amorphous, this abstract concept that's energy changes between these 2 points. Okay? So, for starters, if we start at point A and end at point B, I'm going to take this path. And I'm just scribbling on the paper. This is meandering. I have nothing planned. I'm just going around and around and around. And I'm going to end up at point B. Okay? All the while, as this object goes from A to B, say you hold it in your hand, right? Or whatever. All the while, at every single point, there's a force of gravity downwards, right? Or in this case, in the negative Y direction. Force of gravity down there. When the object is over here, there's a force of gravity, right? And I'm going to try drawing these arrows as the same length, right? Because the magnitude won't really change at every point. There's some force, including at points A and B, right? So what's the only thing that does change between points A and B? Well, it's the object's position. So let's calculate now the work done from point A to point B. So the work done by gravity, in the general case, is the force, in this case gravity, dotted with the displacement dr, right? And again, r is a function of x, y, and z. So let's rewrite that like such. Actually, I'll have more room if I do it below. So in the x direction, it really goes x1, right, to x2, but I'm going to just go on to keep it as a and b. We have the force dotted with dx. Same thing for the y direction. And the same thing for z. All right. So let's take a look here. The force of gravity is in the negative y hat direction, right? It's going down. So the magnitude, mg, now we need the direction, negative y hat. And that's dotted with the displacement, which has a magnitude of dx and a direction of the x direction, right? Unit vectors are always pointing in their specified directions. So similar for the y, magnitude of mg, gravity is in the negative y hat direction, and that's dotted with dy vector that has a magnitude of dy and is in the y hat direction. And let me try and squeeze the z component in here. Whoops, negative y hat. Dotted with dz in the z hat. All right, so we're slowly but steadily writing these expressions in a more explicit manner, right? All right, so we still have the dot product in there, so we need to evaluate that dot product before we evaluate the integral. Let's see. So a to b, I'm going to pull all of the magnitudes in front, so mg dx, and now we have negative y hat dotted with x hat, right? The angle in between negative y, which is going down, and x, right, is 90. So therefore, we have cosine of 90, and that works out to be 0. So this entire term will effectively cancel out. For the y direction, can you see what's going to happen? Let me pull out all of the magnitudes. So mg dy. Now we have the angle in between negative y hat, which is down, and positive y hat, which is up. That's an angle of 180, right, or pi. And so this is a negative 1, not 0. So that does not cancel out. And for z, mg dz, now we have the angle between negative y and z, keeping that isometric perspective. They are perpendicular again, so that's cosine of 90. And that is 0 as well. And so we're only left with the y component, right? Just like from the video in last chapter. So now, integrating, we have, actually, let me pull out the magnitudes of negative mg, and now we're integrating from a to b of dy, right? But really, what's a and b in terms of y, in terms of the y-axis? Well, a, we're starting at the initial y height, right? And b is at the final y height. So actually, on this diagram, it's like that, right? We'll call it, I don't know, y2 minus y1, right? Final minus initial. Or you can also call this the height, right? Or the delta h, or the distance, or whatever you want to call it, right? It's the change in height. So let's go back over here, and we can really say that that is, well, negative mg from y1 to y2. And this equals negative mg y2 minus y1. I know this may be painfully explicit, but that's how I am. Minus mg h, okay? And this is the negative delta U. So the work done by gravity turns out to be a negative change in potential energy. And this is only in the y direction. Why is it only in the y direction? Because that's the axis, right? That's the direction that the force is always in. When it's going from the initial point to the final point, regardless of the path, the force is always down. It never changes direction. So the x and the z terms will always cancel. Okay? Will always cancel, and the y term will never cancel. Right? If we're only talking about the force of gravity here. But again, more importantly, this is the total work done from point A to point B, right? Done by the force of gravity. It says nothing about what's happening in between points A and B, right? Again, we're just worried about the start and the end point, right? So that means that this path, I can take a squirrely path like I've written here, and I'll do the exact same amount of work as if I just went from A straight to B, right? Or even if I went from A straight up, that same delta H, to the height of B, I'll do the same exact amount of work. And that's kind of the crux of the, well, potential energy change, right? That's its relationship to the work done, okay? And so this will springboard us into the conservation of energy, right? So this relationship, in conjunction with the fact that it's also positive change in kinetic energy, we'll see with these two equations combined, we can talk about the conservation of energy as a whole, okay? So with that, thanks for watching.